This is a video version of the online tutorial for the freeware QM model-based design tool. The QM tutorial is located online and you can find it by visiting statemachine.com and then clicking on the Products QM Modeling Tool menu. Here you can read what the Quantum Modeler QM tool is, what it does, and how it looks. In the Getting Started section of the QM manual, you can find out how to download QM, how to install it, how to launch it, and finally the QM tutorial, which is the subject of this video. So here I assume that you have already downloaded and installed QM on your machine. I will use Windows for the demonstration, but QM runs also on Linux and macOS hosts. I start QM in the simplest way by double-clicking on the desktop icon, which is provided by the QM installer on Windows. The first step of the tutorial is creating a new model from scratch. Press the New Model button in the Edit toolbar. This will open the New Model dialog box. In the Frameworks panel, select the QP framework type you want to base your new model on. For this tutorial, you leave the default as QP in C. In the Templates panel, you leave the default template None, so that you can start building your model from scratch. In the Name field, type the name of your new model as Blinky. Finally, in the Location field, choose the directory for your model file. You can either type in the path manually, or you can press the button to open the directory search dialog box. For this tutorial, I will place the Blinky model in a temporary directory in a newly created subdirectory Blinky. Please note that the model directory provides also the reference point for the code generation. All generated directories and files will be relative to this model file directory. When you press the OK button, QM creates the requested model and places it in the specified directory, which you can verify with the Windows File Explorer. At this point, the QM tool contains already a rudimentary model, so let me briefly explain the main elements of the QM user interface, which consists of dock windows and toolbars that surround the Multiple Document Interface (MDI) area in the center. The dock windows and toolbars can be individually resized, docked to the edges of the MDI area, or floated as independent windows. Each dock window can be also individually hidden or displayed, which you control from the View toolbar. The QM tool will remember the window arrangement and will restore it when you launch it next time. The most important dock window is the Model Explorer, which provides the most holistic view of the QM model, as it contains all model items in a hierarchical tree-like structure. At this time, the Blinky model contains only the QPC framework item, which provides the foundation classes for building your own models, such as state machines, active objects, time events, and so on. The framework item is locked, meaning that you cannot change it. The next significant dock window is the property editor, which shows the properties of the current item. The current item is an important concept in QM, as you always work with just one model item at a time. The current item is highlighted in the Model Explorer, and its properties are shown in the property editor. So here, for example, the current item is your Blinky model, and in the property editor specific to this item type, you can add some documentation for your model. But going back to the QM tutorial, the next step mentions an alternative to creating a model from scratch, which is to create a new model based on a model template. QM comes with a few pre-installed templates, such as a bit more advanced version of Blinky. For now, I only want to mention that you can add your own models as templates to the list, so that you can have your own custom starting points for your models. So let's move on to the next step, which is adding model items. The first item you need to add to your model is a package, which you do by right-clicking on the Blinky model and choosing Add Package from the pop-up menu. A package is a grouping construct that allows you to combine other model items into a higher-level unit, the package. The most common use of a package is to group together classes, such as the Blinky class you will add in a minute, but a package can also hold free attributes, free operations, and other packages. A new package is first created with a generic name, which you can change in the property editor. Two AOs, active objects, and the stereotype of the package into components. This is because this package will hold your Blinky active object component. The next step in the tutorial is to add a class. In this step, you will add the Blinky class by right-clicking on the AOs package and choosing Add Class from the pop-up menu. In the property editor, change the class name to Blinky, and for the superclass, choose QPC::QActive from the drop-down menu. Choosing a superclass means that you use the object-oriented concept of inheritance to derive a given class from the specified superclass, which in this case comes from the QPC framework. You need to derive your Blinky class from QPC::QActive because in QM, a state machine can be associated only with a class that inherits one of the QPC state machine base classes. By the way, as described at the start of the online manual, QM is fundamentally an object-oriented tool, regardless of the target programming language. Object orientation means that QM models are fundamentally composed of classes, and only classes can have state machines associated with them. If you program in C and object-oriented programming is new to you, please refer to the application note, Object-Oriented Programming in C, which describes how QM implements the concepts of classes, inheritance, and polymorphism in portable, standard-compliant C. But going back to the tutorial, you still need to add a time event to your Blinky class because you need a periodic stimulus to trigger blinking of the LED. In the Model Explorer, right-click on the Blinky class and select Add Attribute pop-up menu. In the Property Editor, change the name of the attribute to TimeEVT and choose the type QTimeEVT, which is provided in the QPC framework. And lastly, change the visibility of the attribute to Private. Now you can finally add a state machine to your class. You do this by right-clicking on the Blinky class and selecting the Add State Machine pop-up menu. Please note that this menu would be grayed out, meaning unavailable for classes that don't derive directly or indirectly from the framework class QHSM. At this point, you can start drawing your state machine diagram. The first step here is to show the state diagram, which you can do either by right-clicking on the SM item and choosing the Show Diagram pop-up menu, or by double-clicking on the state machine item, or by double-clicking on the class item. Once QM shows the diagram, it also shows the corresponding diagram toolbox for adding new items to the diagram. To add a state, for example, you click on the State tool and release the mouse. You don't drag the State tool from the toolbox. Now, when you hover the mouse over the canvas, you can see that your mouse cursor changes to show the State tool. You move the mouse to where you want to place the top left corner of your state and press the mouse button. Next, while keeping the mouse button depressed, you can drag the mouse cursor to the position of the bottom right corner. You release the mouse button. Alternatively, you can just click and release the mouse button immediately. You can then resize your state along each of the 4 edges by hovering your mouse over an edge until the cursor changes shape, and then dragging the edge with the mouse button depressed and then releasing the mouse button. You then go to the Property Editor and change the state name to Off. You also add the entry action BSP LED off to turn the LED off upon the entry to the off state. Since this is actual C code of calling a function, you type it into the lower part of the entry panel. After adding the entry action, the state shape shows e/text in the top left corner, but it does not show the code. To show the code, you can resize the entry action text box by dragging its ear-marked bottom right corner. Please note that the code shows in the second line, below the e/text. You should also note that once a text box is enlarged, you cannot make the state shape smaller than the box. Finally, let me explain the two different edit areas in the entry and exit panels of the state item property sheet. At this point, you have already used the lower edit area for the actual code, but there is also a smaller edit control at the same line as the label entry. This area is for pseudocode, meaning a shorthand summary of what the entry action does. If you provide some text in this pseudocode area, it will be displayed in the diagram instead of the actual code. To visually differentiate pseudocode from code in the diagram, the pseudocode is shown in the same line as the e/text. This feature is designed to reduce the clutter in the diagram only, and the pseudocode has no implications for code generation. You add the other blinky state, on, in the same way as the previous off state. Now let's move on to adding the topmost initial transition, which every state machine diagram must have. In the diagram toolbox, click on the Initial Transition tool. Notice the new shape of the mouse cursor as you move the mouse, with all buttons released, to the diagram window where you want to position the begin of the initial transition shape. Click the mouse and drag it, holding the mouse button depressed, to the edge of the off state. Notice the cursor change when you reach the edge and release the mouse button. Next, go to the property editor and add the action code to be performed when the initial transition is taken. This code arms the time event attribute of your Blinky class, which you access via the me pointer, to generate timeouts in half a second and also periodically every half second. The function qtimeEVT_armX is provided in the QPC framework. Again, you can provide a shorter pseudocode to show in the transition text box in the diagram. The last elements to add to the Blinky state machine are the two timeout transitions between the off and on states. In the diagram toolbox, click on the Transition tool. Move your mouse, with all mouse buttons released, to the state edge where you want to position the begin of the transition connector. Notice the new shape of the mouse cursor. Click the mouse and drag it, with mouse button depressed, to the edge of the target state. Notice the cursor change when you reach the edge. Release the mouse. You can adjust the shape of the transition by dragging each segment independently. In the property editor, adjust the trigger of the transition. By convention, the triggers in the diagram are all in capital letters and without the _sig extension, but QM will add this extension in the generated code. You add the second timeout transition from state on to state off in the same way. Note that in this particular state machine design, you don't need to add any action code to the timeout transitions, because all necessary actions happen in the entry actions to the states. The state machine is complete now, but you can still rearrange the shapes and adjust the canvas around the diagram. The next step of this tutorial is to generate code. If you worked with other code generating tools before, you might be used to the traditional way of generating the classname.h header file, such as blinky.h, with a declaration of every class, and classname.c file, such as blinky.c, with a definition of every class. Compared to the traditional approach, QM turns the code generation upside down, because QM does not impose any rigid file names or the contents of the generated files. Instead, in QM, directories and files are first-class model elements, so the design of the generated code, which is called the physical design, becomes an integral part of the modeling process, just like the logical design is. The first element of the physical design is the directory into which you wish to generate code. To add a directory to your model, in the Model Explorer, right-click on the Blinky model and select Add Directory from the pop-up menu. Next, in the Property Editor, change the generic directory path into dot, meaning that your code directory is the same as the directory of your model. The directory path is always relative to the model. Once you have a directory, you can add files to it. In a real-life project, you would typically split the code into some header files and implementation files. But for the sake of simplicity, this tutorial will put the whole implementation in just one file, blinky.c, which you create as follows. In the Model Explorer, right-click on the directory item and select Add File from the pop-up menu. After the file is created, you can edit its name in the Property Editor. Type blinky.c in the name box and press Enter. Note that the file icon in the Model Explorer changes to C file. Now you can open the file, either by right-clicking on it and choosing Show File from the pop-up menu, or simply by double-clicking on the file. As you can see, the file is empty, so in the next step you need to edit the file. As already mentioned, in QM you provide the content of every file. For this tutorial, the content of the blinky.c file is prepared in the online QM tutorial, and I will explain it in a minute, but right now you just need to copy the content from the tutorial and paste it into your model. The best way to think about files in QM is that they are templates for actual files to be generated on disk. You can insert any code or text into these file templates, such as include directives, declarations, definitions, comments, and anything else that you would put into handcrafted code. All this code will then be literally copied over to the files generated on disk. But the twist here is that you can also direct QM to generate specific parts of the code based on the model items of your choosing, with the granularity ranging from packages and classes down to specific state machines, states, attributes, and operations. You achieve this by inserting the special code generation directives into your file templates. For example, here you direct QM to generate the declaration of the Blinky class. You can then have some other handcrafted code. And finally, you direct QM again to generate the definition of your Blinky class. Once you have at least one file template in your model, you can generate code by simply clicking on the Generate Code button or by pressing the F7 shortcut key. The first time you generate code from a given model, you will be presented by the Code Generation License dialog box. Here you acknowledge that the generated code will be licensed under the GPL open source license, which is the default license used by the underlying QPC framework. For commercial applications, where you specifically don't want to comply with the GPL, Quantum Leaps offers commercial licenses designed specifically for users interested in retaining the proprietary status of their code. After you accept the license, the actual code generation takes only a fraction of a second, even for sizable models. You also get information in the log console, where you can find out which files have been regenerated and whether any errors or warnings occurred. You can go now to your model directory and examine the generated blinky.c file with an editor. To best see the effects of code generation, you can compare side by side the file template in your model with the file generated on disk. At the top of the generated file, you see the comment added by QM, which informs you not to edit the file manually, as all your changes will be lost when the file is regenerated. Below that, you should recognize the literally copied portion of your file template from the model. But then you can see the code generated from the $declare directive from the model template. The code is delimited by the comments starting with $declare and ending with $end_declare. This is followed again by a portion of code copied literally from your file template. And finally, you can see the code generated from the $define directive from the model template. The code is delimited by the comments starting with $define and ending with $enddef. The very last step of this tutorial is to build and run the Blinky code on Windows. Let's start with opening the Windows command prompt and changing directory to the location of your model. Now I assume that you have downloaded and installed both the Qtools collection with the GNU C++ compiler and the QPC framework in the default location C:QP. I copy the QPC directory to the clipboard, and at command prompt use the captured value to set the QPC environment variable. You can also check your path and verify that the Qtools bin directory has been added there by the Qtools installer on Windows. Finally, you can type in the build command, which you can copy and paste from the QM tutorial. Basically, the command calls the GNU GCC compiler to build your Blinky.c with the specific include directories and then links it with the QPC library. As you can see, the Blinky.exe executable has been created. To run the executable, just type Blinky at the command prompt and watch the state of the LED change every half second. You terminate the application by pressing Ctrl+C on your keyboard. This concludes the QM video tutorial. Please refer to the QM online manual for more information.